Hello, my name is Jory Hamilton with Team 4 along with Chris Elaine, Andy Belinsky, and Devin Aror covering our research on cervical spine fracture detection using computer vision. Detecting bone fractures is critical in post-operative and trauma care because delayed or missed diagnoses can lead to paralysis, chronic pain, and long-term neurological complications. Traditional methods rely on radiologists and surgeons to manually interpret CT or MRI scans, which can be time consuming and subjective, varying on experience and level of expertise. The goal of this project is to develop a robust, deep learning model that can accurately detect cervical spine fractures, which will also help assist healthcare professionals to evaluate bone fusion. We explored CNN architecture models such as a simple CNN, faster RCNN, and YOLO, as well as a transformer model, DTR. However, the YOLO model needs further refinement, so we will keep the focus on the other models in this report. The data for this project is from the Radiological Society of North America 2022 Cervical Spine Fracture Detection Featured Code Competition dataset and is open source from Kaggle. The dataset contains thousands of labeled CT scan slices of cervical spine categorized as fractured or normal. We created our own subset of over 28,000 images and hosted it as our own private Kaggle dataset. For EDA, first we verified that our dataset maintained a 3-to-1 normal to fracture ratio overall and per split. We checked that there was no patient level leakage across splits, visually inspected representative slices from each class for quality, variability, and anatomical consistency, and we double checked that all the images kept a consistent dimension and pixel intensity and that the average bounding box size made sense for our image size. We also plotted a heat map of bounding box centers, which shows a concentration in the center of the image. This suggests our detection models should focus on the central region when predicting for bounding boxes.
Hi, my name is Devin Air, and over the next few slides I'll walk through the different model architectures we use for cervical fracture detection. First, we set up a simple CNN as our baseline. It's a 3-block convolutional model trained to classify each CT slice as either fracture or normal. The model learned general bone structure and converged cleanly, but because fractures are subtle, it tended to predict normal most of the time. The next model we used is faster RCNN, which uses a 2-stage architecture with a region proposal network and ResNet 50 FPM backbone. We trained for 10 epochs with an additional 5 epoch fine-tuning phase. During the initial training, the training loss dropped steadily, but the validation loss diverged, showing some early overfitting. After fine-tuning, the validation loss corrected sharply and stabilized, and the model began producing consistent region proposals and meaningful bounding boxes. Next, we implemented a pre-trained detection transformer model, or DETR. It combines a ResNet 50 backbone with an encoder-decoder transformer, which allows it to reason about an entire CT slice at once. To try to mitigate overfitting, we applied some data augmentation, such as random brightness, contrast, and blur. We fine-tuned DETR for 40 epochs with data augmentation, frozen early layers, mixed precision training, and a large batch size of 100. We selected the best checkpoint by F1 score, with an early stopping of 20 epochs. The best model was found at epoch 34, but the training and validation loss curve still showed signs of overfitting. Even though the training loss consistently decreased and the validation loss fluctuated, validation metrics such as fracture recall, precision, and detection F1 score had slight but clear upward trend, showing that DETR was learning to identify fracture regions and take advantage of global contextual information.
Hi, my name is Andy Malinsky, and I'll be covering our model evaluation results. All our models were evaluated on the same test split. For the simple CNN model, despite overall high accuracy, the low recall and F1 scores indicate the model is failing at identifying the minority class. This is a common issue with imbalanced datasets. Based on the confusion matrix, it's mostly learning to predict normal, since that is the most common answer. Let's see if the other models can improve on fracture recall. For faster RCNN, the final checkpoint achieved balanced detection results for precision and recall. The detector successfully identified a meaningful subset of fracture instances while producing a moderate level of accurate bounding box predictions, which means that it learned clinically relevant spatial patterns. This level of sensitivity is consistent with the early performance of two-stage detectors in medical imaging, where fracture regions are small and exhibit limited contrast relative to surrounding anatomy. Our Dieter model functions like a high sensitivity screener. It achieved a 99% patient sensitivity, which means that it correctly flagged almost all patients with actual fractures and correctly localized the box 61% of the time. To get these results using a low prediction confidence threshold, we had a trade-off with a lower precision of 31%. There's a significant level of false positives, but in a clinical setting, missing broken bones may cost more than incorrectly flagging some healthy patients. And here we compare the final test set results for all three models, looking at classification report metrics like fracture recall, precision, and F1 score, as well as the detection metric for bounding box recall or box accuracy. The simple CNN missed too many fractures and had the lowest recall. The faster RCNN provided a balanced performance with the highest precision and F1 score, but only 58% recall. In a real-world clinical setting, this equates to missing roughly 4 out of 10 fracture diagnoses. On the other hand, the Dieter achieved an almost perfect fracture recall with the higher box accuracy, but at the cost of precision. This means that the Dieter model is highly sensitive and results in many more false positives than the faster RCNN. When it comes to choosing the best model, the trade-offs need to be weighed. Do you want a model that generates fewer false alarms, but at the cost of missing fractures? Or do you want a model that misses virtually no fractures, but at the cost of generating many false alarms? For medical professionals, having that safety net with a Dieter model may be the better option, even if it may require more double checking.
Hi, I'm Chris Aline, and I'll be taking us through the business applications of our fracture detection software. So this software will help support surgeons and radiologists and help reduce the overall time to diagnosis for patients. This will be done by flagging high-risk patients and triaging them more efficiently. The software that we are designing can be integrated with current surgical robotic and navigation platforms. So Medtronic, Stryker, Globus, Alphatech, all these companies have robotic platforms and navigation software as well. So typically they're DICOM servers that are compatible with the overall hospital system. So everything can be done over Wi-Fi or Bluetooth. The surgical workflow would be greatly improved because if you know that you can avoid certain anatomy by taking a different trajectory, that will save a ton of time intra-op instead of deciding in situ that you have to take a different approach because of the patient's anatomy. So this is kind of the point of emphasis where surgical workflow is standardized, but the personalized medicine aspect is coming into play through robotics and through AI. So building this AI augmented surgical platform, the 2D and the 3D registration will come into play both for hospitals and larger university systems, but also in the 2D for just plain X-rays to be done in clinics or surgery centers. This is going to change the future of medicine. So in conclusion, the slight performance gaps that we had in some of the models highlight the need for multi-slice or 3D models in order to capture all the anatomical landmarks that are given in any image. Sometimes the rotation, sometimes the depth of the slice can change whether a surgeon will approach this in a certain way. So the foundation for improved architectures and real-world testing is there. And ideally, we would, in the future, use some class balancing. We would sequence the models and we would do bounding box guided annotations and attention to direct surgeons and doctors to show where these fractures are. So thank you for the time. It was a pleasure to work with everyone and it was a wonderful project. Thank you.